Hello everyone, it is my honor to be here to give the presentation. Today, I will present our winning solution to the challenge where a genetic algorithm is used and won the second place of the challenge. Here is the outline of my presentation. First, I will briefly introduce the background of the challenge. Then we will go over the environment configuration of the challenge. And then our solution algorithm and tricks for improvements are explained. And at last, we will give a conclusion. In January 2020, COVID-19 is declared by the WHO as a public health emergency of international concern, the highest level emergency response for infectious disease. Nowadays, the number of infected cases is still accelerating in the whole wide world. In order to end the global pandemic, multiple intervention strategies can be applied, such as social distancing, contact tracing, and so on. Under such a circumstance, PAPW 2020 hosted a challenge. The challenge is to look for effective human mobility intervention policies to contain an epidemic. Let's go over the environment configuration of the simulator. It simulates the human mobility with one simulation step corresponding with 1 hour in the real world. In the simulator, an individual's health status includes 5 stages: suspectable, pre-symptomatic, symptomatic, critical, and recovered. And there are 5 levels of mobility intervention: no intervene, confine, quarantine, isolate, and hospitalized. And 5 scenarios are tested, and the score considers the total number of infected people and the intervention on human mobility. To generate our solution, we use a genetic algorithm to find out the intervention strategies. GA are a family of computational models inspired by evolution. Generally speaking, a basic GA contains the following procedures: initialization, evaluation, and evolution. In the evaluation stage, there are crossover and mutates among different generations. As shown in the figure, we consider each strategy as a joint of 2 gene segments. One generation is broken down into a crossover phase and a mutation phase. In the crossover phase, partial exchange of strategies is executed, and in the mutation phase, we carry out independent mutation for each element in the strategy to generate the offsprings. And here is the strategy templates. We make a variant version from the quick test. And by applying the strategy, scenario 1, 2, 3, and 5 can achieve a score of around 2.5, while the score of scenario 4 is about 6.7. Naturally, we wonder if there is any room for further improvement in scenario 4. It is noticed that we only use the information of individuals' infection state, while the information of probability from infected is left. Consequently, to further improve the intervention result, the situation of both acquaintance contact and the stranger contact are substituted by 2 sub-situations respectively, which are distinguished with the aggregated probability of contacts as shown in this figure. And the proper threshold is determined according to the quantitative analysis of the statistics of the experiment process and a grid search in the candidate value range. By applying the refined strategy, the detailed score for the 5 scenarios are for scenario 1, 2.42, scenario 2, 2.64, scenario 3, 2.44, scenario 4, 5.76, scenario 5, 2.43. And we present our solution algorithm and checks for improvement, which is capable to effectively contain the epidemic. A simple genetic algorithm is developed to provide solutions with a variant version of strategy template proposed for the quick test by official. Nevertheless, it remains a lot of work to do for the study of epidemic control. We do hope these findings may inform public health policies for countries and regions to combat the global pandemic of COVID-19. That's all. Thank you.